And next to last topic in all of your chemistry, Electrochem. There's a reason why this was saved till near the end of semester 2, because it uses a whole lot of concepts from chemistry earlier in 1412 and some of 1411. It's just almost impossible to do it. It's not that it's so hard, it's just that you've got to know the tools and kind of be able to navigate your way around. And by the way, the chapter after this is going to be nuclear chemistry. And the reason that could be put in about anywhere, it's just totally different, right? Because everything we've dealt with so far has been basically chemical reactions and not nuclear chemistry. Okay, but that's for another day. This electrochemistry is for today. Okay, the first thing I want to do, like I usually do, is to give you a cheat sheet with a bunch of formulas and things that we're going to go through, and I want you to see them all up front. It's just a really good 30,000 foot preview, so that when you come across these, you'll already have a table where they're all related to each other, and you can kind of sort through it, I think, a lot easier, rather than learning these in bits and pieces at the risk of not pulling it together all at the same time. Right. Okay, so let's look at some of the things that I pulled out that I wanted you to know that would be on my cheat sheet. Okay, first of all, and this is in your textbook, some of the terms that's going to be used. So you're going to talk about charge, you're going to talk about current, you're going to talk about potential, and not so much on the electric field, but these three pretty big. Okay, electric charge. Let's start. Charge on a proton. Okay, 1.6 times 10 to the minus 19th Coulomb. What I want you to know now is there's this thing called a Coulomb. You're going to get comfortable. As comfortable with Coulomb as you are with grams when you're talking about mass. That's going to be our standard unit of charge. And I think that's also the charge, because the charge on a proton and electron are equivalent. Yes, it's also going to be the charge on an electron. All right. What is electric current? That is a movement of charge, right? Like a current of water, it's flowing, it gives you a current. Okay, we have a current of electrons. It's electrons moving from point A to point B, from one part of your car battery to the other part of your car battery. They route it through your starter so that you can kind of use that energy, but that's an electric current. Okay, we normally measure that in amps. All right, it's given the designation capital A, and here's your first thing that's going to start messing you. Okay, an amp. Well, I thought it was a flow. Well, it is. Well, how much flow? Well, it's how much charge flows over a given amount of time. And our standard unit of charge is going to be the Coulomb, and our standard unit of time is going to be seconds. So 1 amp is equal to 1 Coulomb second. So if you got a little window and you're looking at electrons fly by, if you see 1 Coulomb of charge go past your window every 1 second, you say, hey, that's 1 amp. If you start seeing a whole bunch of Coulomb charges fly by your window in 1 second, then you got a whole bunch of amps. Okay. Electric potential. Okay, so what's that? That's the force that we're trying to move the dang charge. Okay, so you got this, you're looking through this little window, the electrons fly by. Well, what's pushing them? What's making them go by? Well, something's prodding them. You got some force pushing it. So if you think about electrons, and the analogy is pretty good, of being like water going through a hose, the electric current is how fast the water is running through the hose. But guess what? Sometimes water flows slow and sometimes it flows real fast. Why? Because you're putting a lot of pressure on it. Okay, well, the rate at which it flows is different, a different concept from how much pressure you're applying. They're related, they're interrelated, but they're different things. How fast water flows and how much pressure you're putting are different things that are measured differently. Well, the same thing is true in electricity. So electric potential is how much pressure you got on the water in your hose. And that's called a volt. Okay, and here we go. That's how many right? So we're going to talk about joules of energy, joules per Coulomb. Okay, so those are the three things. Now, I normally focus on coulombs. Why? Because a lot of these equations have a C in them. And so that's how I'm going to use to relate everything. This is how my brain thinks. I try to link things up so I can use them, right? So I know that this is related to this. Why? Because they both got Coulomb. And this is related to this. Why? Because they both have Coulomb. And also, this one's related to that. So I can express everything if I know coulombs. So already I know when I start doing electrochemistry, I'm always in the lookout for coulombs. Because I know if I know coulombs, I can relate one thing to another, at least in my little mind's eye. Okay. So now let's look down here. So, and then I'm going to show you how I link all these together. And then as we come across them, you can refer back to this page. Okay. So there's three relationships that it's going to give you throughout the textbook. All right. And I want you to see them as one and the same, not a whole bunch of confusing things. Okay. It's going to tell you. And one Faraday is what happens when you have 1 mole of electrons flow. That's a Faraday. So I can make a conversion factor out of this. I could put 1 Faraday in a line and 1 mole of electrons below it, or 1 mole of electrons, comma, and 1 Faraday. Okay, so that's the first thing. It's also going to tell you 1 mole of electrons flowing by is going to give you 96,500 coulombs. There we go. So now I like this because now C is everywhere. So I can now relate C, 1 Coulomb, or I can relate C, a number of coulombs to moles of electrons. So if I know how many coulombs my electrons are generating, how much charge is flying by my window, if I can add up that charge, I can tell you how many electrons flew by. Yes? Okay, and finally, if this two are true, if 1 Faraday and 1 mole of electrons, and 1 mole of electrons is equivalent to, will generate 96,500 coulombs, then I can also, I'm a clever boy, I now know 1 Faraday is equivalent to 96,500 coulombs. So what I want you to see in this little triangle is count on 3 conversion factors. You could make a conversion factor here, conversion factor here, conversion factor here. I found this chapter extremely difficult until you realize that. And then all of a sudden, you can just start slinging conversion factors and solve a lot of this stuff. Okay, so let's daisy chain some things together here. See, I've got Coulomb, so I just want to see everything that I can use Coulomb for. Because I notice Coulomb can be used to relate all of these equations, and it can be related to these conversion factors. This is just me. This is not the textbook. It's spread out. This is just linking it together. If you don't like this, do it your own way. Okay, so I know what? If 1 amp is equal to a Coulomb second, then I'm going to rearrange that and say a Coulomb is equal to amperage times seconds. Yes? Okay, so I'm just rearranging that. Why? Because I wanted to have C by itself so I could relate it to here. Okay, so you can rearrange this and make a conversion factor out of this. If you put everything on the left side and put it equal to 1, you would have this. So I know 1 Coulomb is equal to 1 amp second. Are you confused? Well, you're probably a little confused, but you better not be too confused because this is your end of the second semester of chemistry, and you're supposed to be able to kind of work through stuff like this. Okay, so what else do I know? Right here, a Coulomb is equal to what? A joule volt. So I wrote Coulomb is equal to a joule volt, and I got it out of here. Okay, and so I'm just going to rearrange that. A joule divided by coulombs is equal to a volt. This is the form I'm going to use. If I have this and I have this and it asks me volts, that's what I'm going to use. I'm going to use that equation. If I need a conversion factor, I know what? A 1 volt Coulomb is equal to 1 joule. This is just math stuff. And finally, you kind of dig this out. Sometimes they put a mole of electrons down here, and we'll see that that's useful sometimes to put the mole electrons here. Okay, that's the next thing. So it may be confusing, but basically this is what's going to come up a whole lot throughout the whole chapter. Okay, bits and pieces. So kind of burn this in your head so that pretty comfortable making conversion factors out of these. So these are all conversion factors. All those. These are conversion factors. Those are equations. Okay. These are what you're going to use for dimensional analysis if you do it. And these in the little cloud thing are what you're going to use if you're going to solve things algebraically. Okay, I might as well go ahead and give you this since we're on the delta G and the K thing. And delta G, and I'm on the triangle now. Delta G is proportional to K. And what is the equation that relates those two? At equilibrium, it's delta G equal to minus RT log K. Okay, you learned that earlier. Okay, there's two more that relate to the potential of a cell, of a chemical cell, of a battery. And it's this. Delta G is equal to minus NFE, the cell at equilibrium. Okay, so I'm just giving you these now so when they come up, you're not freaked. And some of these equations have names. And needless to say, if K and delta G are related, and if delta G and E are related, then there must be a mathematical relationship between K and E, and there is. And it's the equation that I have spinning, that's shown just above the spinning wheel there. Okay, so that's kind of the cheat sheet of the things that we're going to use. And I can't switch slides until this stops now. You may remember this from your textbook, or this. So we know that if we know grams of anything, we can count the stoichiometry thing. Here's what I want you to see. It took me like my third year in chemistry major. Nobody ever showed me this. It's like, man, this would have been nice to know. Because I kept thinking I was learning new things. Well, look what you could do with the ideal gas law. The ideal gas law is just another way into the mole hole. That's all it is. Any equation you can solve for N. And guess what you're going to be asked to do later? You're going to be given delta G information. And guess what you're going to be asked? How many grams of this are you going to need? And it's going to seem so difficult. And it shouldn't. Instead of going from gram to mole to gram, you're just going to go from delta G to N to mole to G. So N in a lot of these equations is MOL earlier. So all of this stuff, even ideal gas law, it's just another way into the mole hole. That's all it is. So don't overthink this stuff. When you get into the stoichiometry, that's the thing people missed most. And it's the thing that they shouldn't. It's actually quite easy if you come back to this diagram and realize, oh my gosh, I just have to find some equation that has moles in it. I'll calculate moles, and then I'll just do everything else normally. Okay, now let's get into the topic of this, now that you've got some background. Cells, basically we call them batteries. Okay, there's a slight difference, but let's talk about there's two types of cells. There's a voltaic cell, also called a galvanic cell, and that's what you would know as a battery. And that's where electrons flow naturally from one pole to the other. Okay, so that's it. That's how a car battery works. Now there's this cell also called electrolytic cell. All right, and that's where you're forcing the flow. So look at the diagram here, and let me show you what happens in your car battery. So you have part of your car battery, and electrons flow from one part to the other, from the anode to the cathode. And it's flowing naturally, so that's a voltaic or galvanic cell. And that's good. And by the way, this electron, like I told you earlier, is routed through your starter, and that's why your car starts, is because that's what we do. We use batteries and they trick them. These electrons want to get from the anode to the cathode really, really badly, and they'll do whatever it takes. So if you connect them with a wire, they'll just go wherever that wire is. And if you run that wire through a starter, then by golly, it'll start moving wheels and things if it has to. It's going to do whatever it takes to get from one to the other. Okay. But what happens with your car? Well, your car battery will crank, I don't know, probably about 15 times if you don't charge it back up. And you charge it with an alternator. So here's what happens. So it's almost like putting a power source or another battery in line. And what you're doing is you're forcing now the electrons uphill. So the electrolytic cell, if you will, is kind of that non-natural, that uphill. But it's still a cell, because electrons are flowing. But you're having to add force to it. So here, the water is flowing downhill naturally, voltaic. Here, you're having to pump the electrons uphill, okay? And so sometimes you can use even either battery or a battery charger or alternator, whatever. And I normally just call those an electron pump, just like water. You're just having to pump it somewhere. You're having to apply energy to pump it. And what you have to do is you have to apply more energy to get this uphill than it does for it to flow downhill. So anyway, so we have an electron pump. All right. So let's use zinc and copper. Zinc is more active metal. So that means electrons will flow from zinc to copper. So the more metal, the more active one is the one that gives up electrons. That's why sodium explodes in water. It's giving up electrons. Big time. Big time. Okay. So you want to remember that. Your more active metal is the one that naturally in a voltaic cell is going to give up electrons. And your least active one is the one that has to take it. So it's kind of like stronger. Think about it as being more active, as being physically stronger, where you can force somebody to take something. And the thing you're forcing them to take is electrons. Okay. And your less active copper is kind of your wimp. Okay, so if zinc says you're going to take this, then copper, you're going to take it. Okay, so let's look at what that means. First of all, what's being reduced? Copper. Reduction is gain. What's gaining electrons? Copper. Therefore, copper is the cathode. Red cat. If this is the cathode, then this is the anode. Anode is where oxidation occurs. Okay, that's easy. So, but what's your negative and positive pole? Well, we just said zinc is more active, so that is your negative pole, and copper is your positive pole. Well, now let's look at the next scenario. Let's turn that into an electrolytic cell. We still got copper and zinc, but we're going to have an electron pump, an alternator, and we're going to pump the electrons back. Okay, so what happens? Well, guess what? Now all of a sudden, zinc is your cathode. Why? Because it's gaining the electrons. It's reduced. So your cathode has switched poles. How about copper? Well, yeah. Well, now electrons are leaving that, so it's oxidized, so that's now your anode. Okay, so the flow of electrons is different. Now all of a sudden, your cathode and anode have swapped. But what didn't swap? Your pole designations. Why? Zinc is zinc and copper is copper. And we said zinc is more active than copper, so zinc is negative and copper is positive. And in this other one, zinc is negative and copper is positive. So these are telling you different things. You have been warned. Okay. I probably wouldn't beat a dead horse on that, except it messed me up so many times. Okay. Now let's look at what a battery looks like. And the first thing I want to do is look at voltaics, because it's kind of natural. It's batteries. It's things flowing in the natural direction. To me, it's a lot more intuitive. I think the textbook might go into electrolytic cells first. So beware. Okay, so let's look at voltaic or galvanic cells. So let's look at copper and silver this time. Now, it just so happens copper is more active than silver. Well, we know silver is not very reactive at all, right? Okay. Why? That's why we use it in teeth fillings, right? Because it's not very reactive. If silver were very reactive, it wouldn't make very good filling now, would it? I mean, you'd be grabbing your tooth all the time because you'd have reaction going on in your teeth and it'd hurt. All right. So silver and gold are typically inert. They're about as passive as you can get. They're about as less reactive as it comes. So here we go. So copper is more reactive. So what does that mean? If we make a battery out of these, electrons are going to go from copper to silver. And if you got a little voltmeter there, you'll actually see a little peg. As the electrons run through there, there's a piece of equipment. It makes them turn a little wheel, and your voltage goes up. Okay, what's actually happened? Now here's the key thing. So as electrons leave, what's happening? Copper is getting turned into what? Copper ion. Yes? Right. So let's look at it over here to the right. Copper is being turned into copper ion, and it gives off 2 electrons. So for every atom of copper, you can give up 2 electrons, and they can flow through here. Yes? Okay, but what else happens now? Well, as copper becomes copper 2 ion is soluble in water and it kind of breaks away, so you can kind of see corrosion occurring. And that's why, and that'll be part of something we'll talk about another time. But that's all what corrosion is. That's what corrosion is. It's where some metal is going to an ion and the ion is breaking off or it's dissolving in something. And so what you're going to find out is your copper plate gets smaller and smaller. What's happening over here? Oh my gosh. Is this plate actually growing larger? Well, yeah, it is. Really? Yeah. So this is how you silver plate something. You put it in silver solution, you run a bunch of electrons in it, and the silver ions will grab a hold of those electrons and it'll plate it out. So anytime you silver plate something, of course it gains weight. Well, how does it gain weight? Well, it's gaining silver, for Pete's sake. If you got a piece of metal and you silver plate it, you're putting more atoms on it, so it gains weight. So this is what happens in an electrolytic cell, in a voltaic cell. Something is corroding. Something's getting smaller and something's getting larger. Well, it makes sense. You got mass balance and all that stuff. Okay. So here's how I kind of picture it. So these electrons come down to this piece of metal, and of course, Mother Nature wants things to be neutral. And so, well, where's she going to get a positive charge? I know. I'll look in the solution, and the positive ions in here will plate out. And so now the silver electrode is growing and the copper one is shrinking. Now you do have to connect the circuit through a salt bridge. All right, so here's what happens. So you're going to have like copper, maybe your original solution was copper nitrate, or you're making copper nitrate. Well, what's going to happen is you're going to build up more and more positive charges, yes, and you're going to need to neutralize those, or you'll have just too much charge to build up and it won't work. So what happens is there's some nitrates over here. Negative ions will come over here through this, what's called a salt bridge, and negative charges will come so that when you form positive charges, you got a back alley, a back trench, to where some negative charges can come over here and make this solution charge neutral. Likewise, as you chew up, as you remove positive ions here, you now have a shortage of positive ions, so you'll have sodium ions come from here and travel that way. And so what we had here was solutions of what? Sodium nitrate solutions. Why do we have sodium nitrate solutions? Because these are ionic solutions, and we wanted them to be able to flow so that when we built up or lost charge, we could replace those and keep both solutions charge neutral and keep the battery going. There we go. Okay, so with that, this is what it looks like. This is picture speak for battery talk. Yes, and now let's go to equation speak. Okay, so what happened in this cell? Copper went to copper 2 and 2 electrons. How do you know that? Well, I know from Gen Chem 1. Copper goes to copper 2. And if it goes to copper 2, it must have given up 2 electrons. Okay, fine. What's happened at the other? Well, one silver, every silver gains 1 electron and goes to an atom of charge neutral silver. Yes? But here's one thing you got to realize. If every time you lose an electron, what happens in a redox reaction? Every time you lose one, something else has to gain one. So here we go. If we lose 2 electrons, if copper loses 2 electrons, how many electrons have to be gained by silver? A total of 2. So to account for the 2 electrons, I have to have 2 silvers, and I'm going to make 2 silvers. And now you can see these cancel out. And that's the key to balancing and doing electrochemistry. One of the keys is that the number of electrons lost, notice this is on the reaction side, has got to be equal to the number of electrons gained by something else. And if it's gaining it, it's on the reactant side. So that's going to be equal. And that's why there's no electrons shown in that equation at the bottom. So I don't show those. That is the equation, but I know that they were there. Now, these 2 equations that we use to put, and this is like a Hess's law thing, right? I'm just adding this reaction and that reaction, and I'm getting the actual chemical reaction of what's going on. Okay. Let's see. What I wanted to say about that. Right. So you can see that what's happening here. Let's pull it all together. Well, that's oxidation. Oxidation is lost, right? Oil rig. If that was oxidized, I know the other thing must have been reduced. There's my oil rig. And I also know something else. Red cat. I know if this is reduced, that's the cathode. And I know if that was oxidized, that's the anode. So now I can pull a simple reaction together. And each of these is called a half cell. Yes, because that's half of what's happening. So a half cell is either your oil piece or your rig piece. So we can separate those and slice and dice those. And the key is to make sure that each of them has the same number of electrons. There we go. Next thing. This is really clumsy, this picture. You don't want to draw that every time. And these equations, well, that gets kind of tough drawing that every time. So there is what's called a shorthand, a cell notation shorthand. So let's walk through that. You do anode cathode. So what happens here? Copper goes to copper plus 2 at your anode. So what this means right here on this left side is you're supposed to see in your mind's eye everything in that picture on the left side. And that's telling you copper is going to copper 2 ion. And of course, it's not going to show electrons because this is representing your overall cell and you know they're going to cancel. And what's happening on the right side? Silver ion is going to silver. Okay, so there we go. So you've got what's going on at your anode and what's going on at your cathode. All right. Our coefficients are ignored. This really is a shorthand to just kind of let you see. If you want to know how many electrons, notice that's going to positive 2, that's going to positive 1. So this is not showing you a balanced chemical equation. It's not taking into account coefficients. It's just trying to show you what is at the anode and what's happening to it and what's happening at the cathode. Okay. For example, use cell notation to describe a cell in which copper 2 ions are reduced to copper and zinc metal is oxidized to zinc ions. It's pretty easy. Just draw that out. So what's happening at copper? It just said copper 2 ions are reduced. Reduction is gained. So how many electrons is a copper 2 going to gain to become copper? It's going to gain 2. So there we go. Reduction is gain. It actually said the word gain, so that's pretty easy. This is reduced. Yes. I can also tell you what, that's your cathode. That is the cathode. Why? Because of red cat. Okay, so what's the other one? And zinc metal is oxidized to zinc ion. So this is really easy. It's just describing what. So zinc goes to what? Zinc plus 2. How do you know? Because that's a type 1 metal, and zinc can only go to zinc plus 2. Okay, so if it goes to zinc plus 2, then how many electrons must it have given up? 2. Okay, so there we go. So since it gave it up, it was oxidized. So there's your oil rig, there's your cathode, there's your anode. And now that you know that, you can do this. What's going on at your anode? What's going on at your cathode? At your anode, zinc is going to zinc 2. At your cathode, copper ion is going to copper. So there's your shorthand notation. Pretty easy stuff there. Which one are you going to use? I don't know. Sometimes the shorthand is just a lot more handy. Sometimes you need to actually do the equation so that you can calculate the number of electrons. Let's see where we are. Okay, let's see. Using AMP to calculate time, we'll do one question in the last few minutes we have left. I've just redone all of this to remind you. I think I have one more thing. Okay, I've kind of labeled some of these. Remember, that's the movement of charge. You can kind of see something. And there's the force. So as you do these, kind of keep in mind so that when you read a question, if it's getting at one of these two things, you kind of know where to go. Okay, and we got the charge on a proton. So let's work one right quick. Calculate the atomic weight. Really, you can do that? Calculate the atomic weight of calcium. Well, how about I look on a periodic chart? Well, how about you don't? Okay. We don't have it. It's missing from our periodic chart. What's the atomic weight of calcium? Knowing 0.0324 Faradays was needed to produce 0.651 grams of calcium. So here's what happened. I'm doing a reaction. I've got calcium ion, and I'm pumping a bunch of electron into it, and I'm what? Producing calcium. How much am I producing? 0.651 grams, okay? So I see these electrons flying by. I'm counting electrons, and that's one way to do is just pretend you're looking at a water hose, except instead of water, it's electrons flying by. And you could measure either the rate at which they're doing, or you've actually got a pressure gauge here. Sometimes you can measure how much force is pushing it. In this case, you could measure Faradays. So how could I get there? How could I get to atomic weight from that? Okay, running short on time. Let's look at that. First thing you do is you're going to want to look, what are you trying to calculating? Where is your box at? Your box is right there. Box equals star. That's what you're looking for. Atomic weight. So, by the way, almost all these can be done with dimensional analysis. I can't even do them the other way, I don't think. So what do I know? I need to know how many grams of calcium there are. I need something that tells me how many grams of calcium, and I need to tell me how many moles of calcium that was equivalent to, and I can plug those in and I can tell you what? The atomic weight, the molar mass, right? I hope you see that as dimensional analysis speak for what? The atomic weight or molar mass. Okay, so what do we know? This is the only thing that was given right there. So I put it over 1 because it's given. Okay, now what I have to do, oh, that's great, because look, I already have part of it done. I'm looking for grams in the numerator, and I've already got grams in the numerator. Well, that was pretty easy. All I need to do is look up here and find moles, and I'll plug it in, and I'm done. Oh my gosh, it doesn't give me moles. What does it give me? Well, it gives me Faradays. Well, guess what? Either this is not workable, or you're going to have to be able to find a way to relate Faradays back to moles. And it just so happens that you can. Why? Because using the relationship I showed you earlier, you know that for every 1 Faraday, there's 1 mole of electrons went by. So, since you know there were 0.324 Faradays, you can relate that to moles. So there we go. So that's a given, and you can now relate that to moles of electrons. Yes? So let me see. Let's see how bad that'll... Okay, so I'll just point to it with this, right? So why did I put this down there? Because I'm going to use this value to calculate moles. How did you know I could do that? Well, 1, I'm showing you how. But 2, if you look back at that little triangle I gave you, you would see that was a conversion factor. 1 Faraday is equivalent to 1 mole. But so do I stop there? Well, you could, except what? The unit of moles of calcium hasn't shown up. You need moles of calcium in the denominator. And what do you have? You don't. Right now, you've got moles of electrons. Well, grams of calcium divided by moles of electrons is not the atomic weight of calcium. Atomic weight is the grams of calcium divided by the moles of calcium. So I'm just going to convert moles of electrons to moles of calcium. How so? Well, I have that relationship right here. I know for every 1 mole of calcium, it's going to consume 2 moles of electrons. So again, I'm just doing the simple thing that we always know to do. We're just taking the coefficients of our chemical equation and we're converting them into conversion factors. And now notice everything is canceled out on the bottom except for what? Moles of calcium. And now I have it. And my units work out. Okay. And that's the wheel of death. And that's probably enough for today.